Today I've got two RPKI related topics, RSCs and ASPAs, and two Whois related topics, NRTM v4, and some updates we are in the process of making to our RDAP service. So first is RSCs. RSC stands for RPKI Signed Checklist, and it's a new object type in RPKI that allows for packaging together a signature over a set of files and then distributing that to a third party. So to generate that, a user takes a set of files, hashes the file content, signs the file names and the hashes, gets it together into an object, and then sends it to somebody who wants to verify that it's been signed by somebody who has a certain set of IP addresses or AS numbers. And this is useful for a couple of different reasons. The first thing is that it can be used to sign arbitrary files. So unlike, for example, Whois, where the data structure is very narrowly drawn, this is more flexible. So it can be used to support ad hoc and people-driven processes. A related point is that there's no need to publish these objects in the public RPKI repositories. So that's also unlike with Whois and some of the other record types. And that means that if you have some sort of business operation that you'd prefer remain private that would depend on these objects, then this supports that sort of thing. There are a few different scenarios where this could be useful. The first one is bring your own IP services. The second is with third-party database registration. And the third is with custom RPKI applications. So bring your own IP services, for those who aren't familiar, this is something offered by some of the larger cloud providers like AWS, Azure, and Oracle Cloud. And it allows the use of your own IP addresses that you've got, say, from a regional registry in BGP on the cloud provider's infrastructure. And there are a couple of different reasons you might want to do this, but the main one is that it allows you to avoid charges associated with use of the cloud provider's addresses. So on the left-hand side of this slide is the documentation for AWS's BYOIP enrollment procedure. And it's not that they can really do anything about this because they need it to work across different RARs who have different systems, and there's no existing signing infrastructure they can make use of, so you have to do things like generate keys and so on. But once RSCs are implemented, if they were... this whole procedure could reduce potentially to something like get token from cloud provider, sign it into an RSC object, send that back, and then create Whois for the cloud provider's ASNs. And that should help to simplify things in this space. Third-party database registration, a good example here is something like PeeringDB. If you go to register your ASN in PeeringDB today, then the way that they check that you can speak for the ASN is that the domain of your registrant email address matches one of the domains in the Whois object for the ASN. So it is a check, but it's not exactly airtight. So if that were changed to use something like RSCs, then that becomes more robust and reduces the chance of mistaken or malicious data getting into their database. And somewhat more abstractly, this functionality can be used to support custom RPKI applications. So if you have some idea for, say, within your own business or within some sort of closed group, some application that might make use of RPKI signing, then you can offload the construction of the object and the verification of the object to the RSC processes. And along similar lines, if you had some sort of idea that you might want to take to IETF and get an actual signed object done, this could potentially help with prototyping. The current status of this work, the specification was published in November of last year. There's production code in RPKI client, which is the RPKI validator that is maintained as part of the OpenBSD project. There's quite a bit of proof of concept code on GitHub. And at APNIC, we were planning to implement this earlier this year, but it got deferred in favor of other work. so we will be looking at it for next year. The other RIRs support this work in principle as well, so if you are interested in seeing implementations from them, please let them know. Okay, the next object type is the ASPA, or Autonomous System Provider Authorization Object. And this is something that's signed by a network operator. It contains their ASN as what's called the customer ASN. And it then lists all of their immediate providers as provider ASNs in the object. So the object contains the one ASN for the customer and then a set of ASNs for the providers. And other network operators can then retrieve those objects from RPKI and use them in a route classification process, and then that classification process turns out routes as being valid or invalid or unknown, so similar to how the route origin validation works. And then valid routes can be preferred to unknown routes, and invalid routes can be dropped. So a similar sort of process there. The main reason this is useful is that it can be used to detect and mitigate route leaks. The adjacency information can be used to, at least in some cases, determine that there's a valley in the route and that therefore it should be dropped. So compare route origin validation, which is just about the origin. So it's just about making sure that the beginning of the route is correct. Something that falls out of this adjacency information is that it's possible to protect against certain types of forged origin and forged path attacks. And in particular, the attacker, to try and get around this constraint, has to add extra ASNs to the path. So that makes the path longer and less likely to be accepted. There are two validation algorithms in the documents. One is for when you are upstream of the next ASN, and one is for when you're downstream of the next ASN. The upstream validation algorithm is simpler, so I'm going to go through that first, and then followed by downstream. So the process here at a high level, if the AS path has a single entry, then it's valid. If the AS path contains a hop from a provider to a customer, then it's invalid because there's a leak. If the AS path contains a hop without an ASPA, then it's not possible to say one way or the other whether it's valid or invalid, so it has unknown status. Otherwise, all the hops are going to be from customers through providers, and the route is valid. So the simplest case here is when you have a receiving AS that's upstream of the origin. So the ASPA state in this case is irrelevant. The receiving AS knows what its relationship is with the sender. It's not possible for this to be a route leak, and it's declared valid. However, if you add another AS to the path and there are still no ASPAs, then it's not possible to determine validity anymore. If AS1 in this case is actually a provider for AS2, then you have a leak, so this becomes unknown. Of course, if AS1 adds AS2 as one of its providers in an ASPA object, then this is valid because you have a hop from provider to customer 1 through 2, and again from 2 to the receiver. If AS1 lists some other provider in an ASPA, though, then there's no longer a hop from a customer to a provider, and it's possible again to determine validity, but it's invalid in this case, so it will be dropped. The downstream validation algorithm is a little bit more complicated, but again at a high level. If the AS path has an up ramp from customers through providers, followed by a down ramp of providers through customers, and there are no hops in the middle at the top between the two ramps, or there's one lateral hop, then the route is valid. If the AS path contains a valley, so again hop from provider to customer followed later by a hop from a customer to provider, then it's invalid. Otherwise it's not possible to determine validity, and it has unknown validity status. So again, the simple example, when you have the downstream receiving from the origin, the ASPA state's not relevant, the receiver knows what its relationship is, and it's not possible for this to be a route leak. But in the 2AS in the path example, even though there are no ASPAs, it's also not possible for this to be a route leak. So this is also declared valid. It doesn't matter whether AS1 is a provider for AS2 or a customer of AS2. However, if there are three ASs in the path and no ASPA objects, then it's no longer possible to determine validity. Fortunately, it doesn't take many ASPA objects for things to become valid. So if AS1 issues an ASPA for AS2, it's no longer possible for there to be a leak, and this becomes valid. And the mirror image of that is if AS3 were to issue an ASPA for AS2, the same thing applies. And of course, if they both issue ASPAs, hooray, it remains valid. And this example helps to illustrate that idea of the up ramp followed by the down ramp. The next question might be, well, what does AS2 do? It doesn't have any providers. And the documents specify that if an AS has no providers, then it should publish an ASPA object with AS0 as the single provider. In this case, it's already valid, so that ASPA doesn't help as such, but there are some instances where that can be useful. And of course, communicating intent here is a useful thing anyway. So getting to an example that comes up as invalid, if AS1 has an ASPA object, but it doesn't include AS2, it's still the case that this is valid because it doesn't matter whether AS1 is a peer of AS2 or a provider for AS2, everything's going to be fine. However, if AS3 stops publishing its ASPA, then it's no longer possible to determine the validity status. And if AS3 starts publishing an ASPA that points to some other ASN, then there's a leak. So this becomes invalid. And a somewhat more conventional example of a leak here is where all the ASPAs are actually configured correctly and the route is traveling across a path that makes sense as far as the ASPA objects are concerned, but AS3 is actually leaking stuff to AS4. So there's still that valley, and this is invalid. So with the attacks, with how this helps with attacks rather. So if you have an attacker trying to, they're targeting AS1, so they're constructing a route, they put AS1 as the origin, and then they put themselves as the next AS in the path. If AS1 has registered an ASPA and the receiver, or rather the recipient of this route is doing upstream validation, then the recipient is going to reject the route because the attacker's AS is not listed as a provider for AS1. Hooray. So the obvious thing for the attacker to do is add one of those provider ASs in the path between AS1 and between its own AS. But of course, this makes the path longer and less likely to be accepted. And there's this recursive aspect to it where if the provider AS itself has an ASPA, then the attacker needs to add more ASs to get the route to be valid, again making it longer and less likely to be accepted. So that's a useful property of this as well. As far as risks go, something we saw with origin validation in the earlier days with people being reluctant to turn it on was that they thought they were going to get support burden out of it. We don't think that there's going to be much risk associated with turning something like ASPA validation on. It is true that a single mistaken ASPA change is going, or can potentially knock out everything that goes through that AS, but there are lots of things that can knock out a single AS, so it's not a big change in that respect. And if you have a single point of failure dependency on one AS, then that's not going to, your posture isn't materially affected by how ASPA works in that sense. Another consideration here is that for Apex ASs, the ones right up the top, the ASPAs, ironically, sort of, don't have much effect in practice. So it's not possible to knock things out by stuffing up an ASPA right at the top of a path. The current status of this work, there are two documents in IETF working group last call. There's quite a bit of production code. There's the CRIL CA and the RouteNator validator, which are managed by NL NetLabs. There's the RPKI client validator, which was mentioned earlier. There are two software routers, OpenBGPD and the NIST test router. And but there's nothing in the sort of hardware space, nothing Cisco, Juniper, etc. At the moment. RIPE have an API for creating ASPA objects in their test environment as well, so that's something else that can be played with. One thing to keep in mind here, though, is that these documents aren't final yet, and they have changed a little bit over time. And in particular, there are some pending updates to Krill and RouteNator, and possibly also OpenBGPD to match the latest specification. So things are still a little bit in flux if you wanted to try this out. And for APNIC, we're planning to implement this in next year. The next thing is NRTM v4. This NRTM stands for Near Real-Time Mirroring, and this is a protocol for maintaining a local copy of a Whois or IRR database. So this can be useful if you want faster queries than you get from the remote end, or if you want to be resilient to failure in that remote service, or if you're doing whole data set analysis, this sort of stuff. And v4 is a successor to earlier, less formal versions of NRTM. So why is this useful? NRTM v3 and the earlier versions have various problems. The response structure is ad hoc. It's a line-based, text-based protocol, so much like port 43, who is proper. There's no formal documentation. There's no specification. The way that errors work is not necessarily that clear. The way that end of stream works is not very clear. And another thing is that the initial state is not handled in bands. So you have to go and get some snapshot from somewhere, seed your system with that, and then use NRTM to keep it up to date. But for example, with APNIC service, you can get updates for the previous 2 weeks, but if you fall out of sync for longer than that period of time, then you need to set things up again, and it's a bit of a pain. NRTM v4 addresses these problems. It's an HTTP-based protocol. The responses are JSON, so it's very easy to work with. It's going through the standardization process at IETF, so that helps as far as stability and consistency in implementations are concerned. All of the data is signed, so with NRTM v3, it's just plain text, whereas with this, you can actually verify that the server sent you the update. And it's based on RDAP, which is the distribution protocol for RPKI, and that includes snapshots in band, so this does as well. And that means that clients can be set up to reinitialize themselves in the event that they get out of sync. So that should make things easier for clients as well. The specification is currently being worked on at IETF in the GROW working group. It's not in last call or anything like that yet, but it has been kicking around for a while, so hopefully not too much longer there. RIPE have a test service with their production data in it, so it's possible for anybody who wants to try this to play around with that. The document itself, the principal maintainer is, or rather the principal author, is also the maintainer of IRRD, which is software that can be used to maintain a local copy of Whois or IRR database. So there'll be an implementation in that at some point, so that will be useful. At APNIC, we're actually transitioning our current RIPE service NRTM, RIPE-based NRTM service to use IRRD. So hopefully when they update their implementation, we can just pull that in and start providing it for free. And the last thing I have today is about RDAP. So for those who aren't aware, RDAP is the successor to port 43 Whois. So it's available over HTTP, responses are JSON, it handles redirects, basic sorts of things that APIs do these days. It was implemented by all of the RIRs 5 or 6 years ago, but after we did the implementations, we realized there was some inconsistency in how each RIR had done things. So we got together and did a profile, and that's now been implemented by all of the RIRs except LACNIC, which is the Latin American registry, and they'll be doing that later this year. So what the profile does is it just improves consistency, limits flexibility where we don't need it, and makes things easier for clients. So it further documents how redirects work, tagging resources as delegated or not delegated, and also confining the contact data in particular, because RDAP uses a vCard-based encoding, which is very flexible, and we don't need most of what that provides. Also in the RDAP space, we have the reverse search document, again through IETF, and this is about providing operations like finding resources associated with a given contact. So each of the RARs provides something like this today via Whois, and we want people to be able to transition from Whois to RDAP if they want to. So we're looking at providing that functionality in RDAP as well. And the other document is this RAR search document. So a similar sort of thing. There are gaps in RDAP that we need to fill for RDAP to be a proper successor to Whois. So in this case, IP and ASN search, extending that earlier reverse search document for internet number resources, and searches for more specific and less specific resources, internet number resources. So the idea here is once we do these two documents and have the profile done, then it's much easier for people to move from Whois to RDAP. And I didn't do a slide for it, but we have also added the geofeed attribute like RIPE have. So previously, if you wanted to add geofeed to a Whois object, you had to do it in a remarks attribute. There is now an actual attribute for that. So that should hopefully simplify things a little bit. And that's all. Thank you.